Hello and welcome to today's episode of the Teardown sessions. I am your host Helen Leigh, and today we have got Ryan Cousins with us for the whole hour. We are going to be talking about FPGAs and his very exciting board, Snickerdoodle, which I think many of you will already be familiar with. So that's all very exciting. But before that goes on, I wanted to share with you a few things that were happening at Crowd Supply before I bring Ryan on. So first of all, I wanted to give a big shout out to our sponsors of today's streams, the delightful AMD-Xilinx FPGA Playground. We have all sorts of interesting things with FPGAs here, lots of giveaways and so on. If you are interested in a Snickerdoodle, we are giving away one in this session today, but also we do have an extra one to give away if you are subscribed here to the FPGA Playground to their mailing list, which we don't use very often. It's maybe, look, here we are. We've done 2 emails so far this year, and we did 2 emails last year. So if you'd like to win a Snickerdoodle, you can sign up there. We've got also some exciting things happening. We've got a Sharpie keyboard, which is crowdfunding right now, which is a QWERTY keyboard, tiny Linux computer with all sorts of exciting things. That is nearly 1/3 funded at just under 1/3 of that campaign going. So if you want to support this lovely open source QWERTY keyboard, Linux laptop, very small little thing, you can do that now. Also crowdfunding now is the Navo Info Micro Hat, which is a little add-on board for the Raspberry Pi from Leon Anadi, who is a delightful hardware creator in Bulgaria. Shout out Leon. So go and support his work if you'd like to. And then there's some exciting things we've got coming soon. This is Quadrant, which I'm quite excited about. I came across this at the Seattle Hardware Happy Hour. One of the guys there, Chris, is one of his projects. And it's an open source time of flight hand tracking interface, similar to a Leap Motion, but open source and much more exciting. So that's coming soon. Very excited about that. You can sign up for notifications there. Another exciting art tech one here, we've got the Pocket Integrator, which is coming very soon. I've actually had a play on this. This is great fun. So if you are familiar with the Pocket operators from Teenage Engineering, lovely little boards, very popular little things. And this is an add-on for it, so that has an accelerometer in it, so you can play your Pocket operators like maracas or drums. It's all very fun, nice little board to try and look at that. Also, we've got coming Bean Counter. If you watched the stream last week, you'll have seen me chat to Nick Poole, who's an engineer at SparkFun, and this is his first solo project. It's a very handy, I'm definitely going to buy one, SMD parts counter for cut tape. Lovely little device. One of those things you're like, how did I not think of this first? And then finally, I want to show you the Thunderscope, which you may have seen as one of the finalists in the Hackaday Prize last year. It's an open source software-designed oscilloscope. Also part, actually, of the AMD-Xilinx FPGA Playground, because that's built with an FPGA, as are many of the modern oscilloscopes. All right, so that's what I wanted to show you from what's going on at Crowd Supply. So without further ado, let me just review. Without further ado, let me bring on Ryan Cousins. Let me add you in there. Hello, Ryan. Nice to see you.
Hey, Helen. Yeah, same
from
to
the
you.
5 minutes ago that I saw you in the green room.
That's right.
Yeah. So would you like to introduce yourself to the people who are watching this stream? Tell us a little bit about yourself and tell us a little bit about the Snickerdoodle, and we will jump off from there.
Yeah, certainly. Hey, everybody. My name is Ryan Cousins. I'm the CEO and one of the co-founders of Critical. Critical actually launched effectively its company, its first product on Crowd Supply a few years back. That product is Snickerdoodle. So I got a little example of it here. Some of you may have seen it already. It's a little business card sized compute module. It has an FPGA on there. With some Wi-Fi, Bluetooth connectivity, a bunch of reconfigurable I/O, kind of designed to be used in any sorts of applications, from computer vision to robotics, remote sensing, communications, a bunch of different things. We can get into some of the specific use cases later on. But yeah, so we've been at it for several years now. Our kind of core competency is deeply embedded systems, edge computing, FPGAs, of course. And yeah, happy to share some more about our story and how we kind of got to where we are.
Well, very exciting, and I've got lots of questions for you. But I would also like, there's quite a few of you watching live, which is fantastic. So what I'd love to hear from you. I've seen some of you pipe up in the chat already with your hellos. Thanks for letting us know that we're not alone. That's good. But if you ask comments and questions, I will ask them live to Ryan, and also. If the way that you win today's Snickerdoodle and the box of mystery hardware, which is in here, lots of exciting swag and the Snickerdoodle, is I've written down a randomized timestamp, and if your comment or question is closest to the timestamp on my piece of paper, then you will win the contents of this box and a Snickerdoodle. So keep your questions and comments coming, please. It helps us feel like we are less alone shouting into our little boxy computers. So let's start off with FPGA. So I've dabbled in some FPGAs. I would call myself FPGA curious, particularly with the new open toolchain FPGAs. But I think there's a lot of people who haven't, who come from the hardware world, who haven't actually been using FPGAs as much as they've been using microcontrollers. I wonder if you could give a quick guide to what an FPGA is and why you'd use it, as opposed to, or as well as something like an ARM microcontroller. Is it just the infinite GPIOs, or like what? Tell us a little bit about FPGAs. Oh, field programmable gate arrays for those of you who don't know. Let's like wind it back for people who don't know what an FPGA is as well. So off you go.
Yeah, exactly. Yeah. So that's right on. So that's kind of where I was going to start. So field programmable gate array. So probably explaining a little bit more about what the acronym and words mean will help guide a little bit of the conversation about what an FPGA is and does. So you can the field programmable, as you could maybe assume, means that the hardware itself can be reprogrammed or reconfigured in the field, meaning you can reconfigure hardware with software. So FPGAs, the GA portion of that, is an array, basically an ocean of gates, as in logic gates. So basically the way that computers make binary decisions, bunch of ones and zeros. So effectively, you can rearrange all the way that the computer is making the decisions in hardware. So if you think of like on the other end of the extreme, you have these kind of general purpose compute architectures. So that's like microcontrollers, microprocessors, things like that. So those, when they ship from the factory, the hardware itself is set and it's going to perform in a particular way. There's no reconfiguring it. What you can do is layer software on top of that, but it's really designed to serve a general purpose. So the overall idea there is, this thing is going to run the same way for everybody. And your software is going to run on top of that. So there isn't really a customization necessarily you're doing to the hardware. It's just running with whatever horsepower you've got all day, all the time.
Yeah, apparently the buzz that I couldn't hear, everybody else can hear it. So okay. Ryan, could you mute yourself for a second? Does everybody hear the buzz still when Ryan is muted, so I'm trying to figure out if it's my end or if it's Ryan's end, because I can't hear the buzz, but Ryan could hear the buzz. All right. So
yeah, I can still hear it when I'm muted for some reason. I could try switching.
You can.
Switching microphones.
So yeah, it's getting louder. This is it's not ideal. I tell you what, I'm going to change my mic in. And we'll see if that makes a difference. Probably won't, but let's. How's that? Can you still hear the buzz? You can still hear the buzz.
I cannot hear it. The audio isn't as good, but the buzz is going.
Yeah, that's because I've switched to my Bluetooth headphones, not my microphone. So it's possible that there was some interference. All right. Yep. Thank you, everybody, for troubleshooting that. Okay, good. Oh, there's echo now, apparently. Oh, no. Okay, let's see. Echo control. Anyway, carry on. I will figure out. If it's my end, I will figure out some audio solutions. You carry on talking about FPGAs.
All right, excellent. So that's kind of the delineation between these kind of general purpose compute architectures, so microprocessors, microcontrollers, all that, and FPGAs. So you mentioned, why would you need that? Oh, still echoing. Echoing but bearable. Well, that's a little bit better.
What's your microphone that you're using, Ryan?
It's this Yeti that I have. I can try and switch it to the display. Might sound a little different, but let's see if
that's the echo cancellation just turned off.
Echoing.
You turn it back on.
That help people? Gone now. All right.
It says gone. It says gone now. Okay.
All right.
Well, we have slightly worse. Who knows? That's never happened before. That's the joy of live streams, isn't it?
Well, it sounds like everyone sounds fine. All right, perfect. All
right.
Yeah, just people. Yeah, that's good. I'm glad everyone told us that before. We.
Yeah, for sure. Thank you.
So, anyway, as far as FPGAs, where, how, why you'd use them, and all of that. So. There isn't any one single, use the FPGA to process the audio stream, exactly. So there isn't any one single use case that an FPGA is or is not good for. So it makes kind of for an interesting argument to make in terms of when it's a good fit. But generally speaking, so there's a few kind of key categories we've key in on. So, Helen, you mentioned the input and output kind of reconfigurability. So that's a really good one. And so one of the things that led us to towards this general architecture that we landed on was we were doing a lot of embedded system, kind of custom embedded system development. So a lot of basic engineering consulting work for a number of different companies, medical device, industrial automation, a bunch of random things. And we found that we were effectively recreating the same core components, basically the same brain for each one of these systems. You need some sort of processing unit. It's tied to a whole bunch of different things in these different systems. You need some sort of external communication, typically wireless these days. So how can we basically take that general concept and productize it? And that's how we arrived at this Snickerdoodle. And so we centered in on the, if people are familiar at all with the Zynq, and specifically the Zynq 7000 series of silicon from Xilinx, which is actually an FPGA SoC, which is system on chip. So what that means is it combines kind of the best of both worlds, if you will, where you have all this reprogrammable, reconfigurable hardware on the same physical chip as these hardened ARM microprocessor cores. So you can use the whole ARM ecosystem. So you basically out of the box, you can very easily get, say Linux up and running or some random operating system. You get all of like the support infrastructure with all of that. But then you can totally customize how that ARM processor is talking to the rest of the world. So with the FPGA itself, it can be used in the most simplistic sense. You could use it as an IO reconfiguration tool. So that's, you can have a bunch of GPI over here, a bunch of PWMs over here, I2C, you can change it into Ethernet, USB, whatever. All these different kind of digital interfaces can very easily be accommodated without changing any of the physical device in which you're programming. So that makes it really convenient for kind of rapid prototyping and development and all of that. In addition to all of that, you can change the way that data is being processed when it comes into the silicon. So what that means is that now that can take on many different forms as well, but that might be, say, some digital signal processing where you might be filtering or decimating some sort of data coming in. Alternatively, or potentially in addition to that, you can have certain software algorithms, what they call accelerated in hardware. So effectively what you're doing is you're taking, say, an arbitrary software algorithm that would otherwise just be running in a regular microprocessor, that is just going to be running using the characteristics of the chip that you're running it on. So like a Raspberry Pi or whatever random example has a kind of a main processing unit, and it's just designed to run whatever it's capable of running all the time, and you're going to get whatever kind of out of the box performance you get on that. If you have an FPGA that you can leverage, what you can do is actually take some of those algorithms that you have and move them into the FPGA to be executed in hardware. So instead of operating like basically in a sequential pattern just over and over again, you can what they call pipeline or parallelize all those processes to run all that stuff in parallel as much as is practical with any given algorithm. And you can get 2, 20, 50, sometimes more acceleration out of the hardware than you would running it purely in software. And that can give you all sorts of benefits, not only in performance, but also kind of the performance per watt is kind of a common kind of metric you'll see when, FPGA marketing material kind of stuff is how do I squeeze the most possible performance out of the smallest, lightest, lowest power package kind of thing. So that gets, if you can compartmentalize things like running some of your motor control algorithms out of the software and into hardware, get a lot better real-time performance, a lot less load on the processor. So that can be offloaded for things that the processor might be better at. So maybe that's like running a networking stack or an operating system or whatever. So that's how this kind of architecture all comes together. And there's some really creative things you can do with all of that in terms of fault tolerance, changing between, real-time operating systems and non-real-time operating systems, all of that. Kind of the list goes on, but that's sort of a quasi short summary of what an FPGA is and does.
That was a really great short summary. I really enjoyed that. I definitely learned something from that. I wanted to talk a little bit about the programmable element of FPGA. So there's a number of, like, having dabbled in a few different FPGA boards. Like I've come across a few different ways to program it, but yours. You can so basically what are the different ways that you would normally program an FPGA, like to change that hardware design? Like I've come across the Python-based MeGen, which is a really nice one, and I've used quite a few other things as well. But I was wondering, like, what your approach is, both as a professional but also with Snickerdoodle.
Yeah, it's a good question. So generally speaking, we lean pretty heavily on the Xilinx toolchain. So kind of at the core of the Xilinx toolchain is Vivado, which you can download for free and use depending on the part you're using and all these other things. Generally speaking, they're free versions of all this stuff. So now they used to charge many thousands of dollars for this stuff, but obviously is a way to get more people into using these parts and all the rest of it. They made a lot of their higher end tools free over the years, which has been great. And a lot of them gotten more and more usable. So Vivado is kind of at the core, and there's some things that hang off of that. So now they're kind of making this transition to Vitis or Vitis, I guess, depending on who you ask. But so they're making things more and more kind of software engineer friendly, I would generally say. So they have, an IDE for all of your kind of software development built into the same tool that you're doing your FPGA development. Now, within that kind of general ecosystem, you can get into what they call high-level synthesis, which is their HLS tool or HLX or whatever. So that is where you're basically taking C and C++ code and converting that automatically or within the tool into HDL or RTL, basically register transfer level hardware description language. I'll try and ease up on the acronyms, but basically into a language that the FPGA understands, so to speak. So that's what's actually used to reconfigure all of the different gates we were kind of talking about before. So now there's even higher levels of abstraction than that, like you mentioned. So people can check out Pynq, which is Pynq, so Zynq with a P. So that is, that uses the Jupyter network to basically create all of these overlays where we are using Python to create FPGA IP and IP, intellectual property. So like basically the stuff that you're programming, you're reconfiguring the hardware with FPGAs is generally referred to as an intellectual property core. So yeah, there you go, Pynq. exactly. So that's right. So yeah, so you can use all these different tools. Now, when you get into some of the kind of open source side of things, that's where it gets kind of interesting. So Xilinx, just bottom line is they don't really have any open source FPGA tools. So Lattice is essentially the main vendor who's taken real advantage of that. So it's interesting because FPGAs are so complex as devices, just sort of just broadly speaking, that it's very easy if you don't know what you're doing. Now, of course, within the confines of the tool, generally speaking, you're not going to just go and blow up a bunch of FPGAs. It's not, they kind of, if you're doing something that can't physically be done on the chip, you won't pass synthesis and simulation and all these different things that the tools have built into them that these companies have spent, many hundreds or hundreds of millions, or in some cases billions of dollars developing. They have those kind of the guardrails, so to speak, in place. Of course, open source kind of, you don't have the guardrails depending on exactly how you want to use the open source, kind of nature of those projects. So you can very easily get into a situation where you're basically just going to melt the silicon and it's not going to work anymore. That's how reprogrammable these things can be. And there's so much great infrastructure built around the tools. Now, that's not to say that I'm not going to say that Xilinx tools don't have problems, because any software infrastructure or whatever tool provider is going to have problems with the tools. It's just kind of how it goes. And that's sort of one of the advantages to having obviously open source communities is now, instead of just the organization itself working on these problems and crossing off issues off of the feature request list and all these things, now you have in theory, well, not infinite, but effectively limitless pool of developers that can hack away at all these random problems. There are a lot of issues.
It's also quite new. Like people, the open source tool chains for the FPGA ecosystem, they're fairly, they are progressing, but it's not like, like the like all the tool chains that have been made available on many of the microcontrollers, so I'd see it as an early stage kind of open FPGA community. So
yeah,
it will grow.
It's interesting. Yeah, and it's interesting.
Software engineers as well.
Yeah, and it's interesting because one of the many issues with some of these bigger open source projects, or especially if they haven't reached kind of a critical mass, is security. So security and reliability. So not only like you're talking about the physical reliability of the parts and all that kind of stuff, but the security mechanisms built into some of these FPGAs are pretty extravagant, because they sell into a lot of, we'll just say, very like mission critical or whatever, industries. So think aerospace, defense, even when you get into some of the backbone stuff for servers and things like that. Not to say that, that isn't the case for the ARM devices and all the rest of it, but some of the, even obfuscating some of the hardware architectures, or in this case, compute architectures, can be a critical security mechanism for, say, defense contractors or the military and things like that are trying to prevent people from cloning devices, be able to easily reverse engineer, figure out how things work, all that kind of stuff. So that's sort of one of the reasons for all of these layered security mechanisms that are built into both the silicon and the tools. So it can get tricky just opening that stuff up to the world, because then you run into all sorts of open source security issues, which there are a limitless number of those that have been exposed in recent years, and I'm sure will only continue to be exposed. So I think it's really cool. Like the stuff that the Lattice is doing is really interesting, because it does really open up the possibilities for open source and getting people more into FPGAs who wouldn't otherwise be. The tools like Pynq have been really interesting. Now we have used those sparingly on projects. A lot of times, if we are building, so we do a lot of like engineering service like basically helping customers. But I can share a couple of those kind of stories as well. But helping customers develop their products around our product kind of thing. If we're doing that and they don't have, say, dedicated FPGA engineers on staff, which is obviously pretty common, a lot of times we'll use the high-level synthesis tools so we can say, hey, your whole code base exists in C and C++. And while you might not be able to, you're not going to build all that stuff from scratch necessarily, although you could, at least when you get that code base to maintain, it doesn't just look like a language you've never seen before. And now you have to hire a bunch of specialists. Now that makes it a lot easier to maintain. So it becomes a lot more practical, even though those tools are specialized. They, in the sense that you do have to know something about how that hardware architecture works and all that kind of stuff. It's at least a lot more accessible to kind of more traditional embedded software engineers.
Yeah. All right. We've got absolutely loads of comments and questions. So I'm going to dive into some of those. I think some of them might overlap. So hopefully we'll be able to answer a few of them. All right. So we've got this gentleman who's asked, as someone who has never touched any FPGA hardware, can the FPGA somehow be used as a third ARM GPU, CPU, GPU softcore? And that's one interesting question. We've got one here saying, is there any major advantage of using one FPGA over another, other than the amount of logic cells? That's a very open-ended question. We've got a couple of questions here about open source tool chains. If you've got any open tool chains that can be used with the board. What platforms your development tools are available for? Gosh, we've got absolutely loads of these. Well, let's start off with, because there's a few entry level questions here. So we've got this one, here. How do you find information on implementing one? Do you have a favorite book to learn FPGAs? That kind of thing. I think it might be interesting. So if somebody was getting into FPGAs and wanted to, what kind of board, what kind of resources would you recommend to someone who's new? I mean, I would say, for me personally, I've done a couple of interesting entry-level workshops, which aren't as, they're not as big and powerful as the Snickerdoodle. I did, Joe Fitz has got a booklet called WTF PGA, which works through, I believe, an icebreaker, which is, I think it's Peter Esdon's icebreaker board. I think so. And then I've also used the FOMU, which was Tim Ansell's. I don't know if you know Tim Ansell, but he does a really great little workshop. Both the FOMU and the WTF PGA were both really nice, entry level. I'm not talking serious courses here. I'm talking weekend workshop kind of level things. So those are the two weekend level workshop things that I've had to go on and really enjoyed. And what would you recommend, Ryan, for people who are looking to really go a bit deeper?
Yeah, well, first of all, obviously pick up a Snickerdoodle. I mean, that goes without saying.
Well, yes,
right,
of course. But, well, can we? Can we though, Ryan?
Well, yeah, that's so I can say this.
You can win one.
Yeah, exactly. So you can win one.
Can you buy one?
Yeah, that's a good point. So by the as a quick aside, I mean, people might watch this later, I guess, but
yes.
watching this in the middle of the insanity that is the semiconductor supply chain situation right now, anyway, I won't get into all of that, but we did fortunately squeeze a few Zynqs out of Xilinx recently. So
did you? How exciting!
Yeah, so we should have some Snickerdoodles available on Mauser by the end of the month. So I don't know.
You're hearing that here. That's very exciting.
Yeah.
I didn't.
Yeah, news is breaking here first.
I know. Yeah.
So yeah, I don't know how that works.
Thank you for bringing us this exclusive, Ryan Cousins.
Yeah, exactly. I don't know how that works in terms of pre-ordering on Amazon and all, or on we do sell on Amazon.
I think you can pre-order. Yeah, you can place the order on Kitesupply, I think, actually.
Yeah. So all that stuff. So but in any case, so assuming you can buy one. We're in terms of resources. So we have a pretty decent number of kind of just open source projects you can check out. We might be able to drop the link in here that have been built by other members of the community, as well as our GitHub has a number of different examples and things like that. So really, it depends on what you're hoping to get out of it. I'd probably have to get back to you on a list of books and all those things to start at, in very specific resources and links and all that. But generally speaking, so one of the nice things about Snickerdoodle and the Zynq architecture in general is that you can start in, less than, we'll say less than 10 minutes, in case it takes you a couple extra minutes to get out of the box. But like in less than 10 minutes, you can pull a Snickerdoodle out of the box, download the image off of our a Linux image off of our website, put it on an SD card, pop it in, you'll have a console up and running. So there's basically zero learning curve there for anyone who's ever messed around with any of these things. And even if you haven't, there's almost still zero learning curve. So that part's very straightforward. And that's one of the really nice things about having that processor kind of pre-built into the hardware. The downside, if you want to call it that, is that overall architecture is, once you get really deep into it, can be pretty it's exhaustive, I'll just say, in terms of the stuff that you can do with it. So there's kind of benefits and disadvantages to having that if you're just looking to start out. Now, there's also ways to just not have, if you don't want to have anything to do with Linux, you can just have a little bare metal application that pops up, so you can still have the console and all whatever else you want to do. And there's some very simple, straightforward hello world type examples that we have posted around, where you can just, you open up Vitis or you open up Vivado. Here's a project you can just load in. It takes a few minutes to kind of, the longest part of that whole process is downloading the Xilinx tools, because they're tens of gigabytes. It's kind of ridiculous, and you have to like sign up. It's like all free, but it's a pain. I mean, it's just the bottom line.
Yeah.
But it is what it is. But so you can start very small, and you can start saying like, all right, I just want to plug in one GPIO and toggle that on and off from Linux type thing, or a little PWM you're using for a little motor controller or whatever. I mean, the list goes on and on, obviously. But
for real.
But so you can. There's also some pretty. If you want to experiment, there was I think a question in there somewhere about running some of like the soft cores in FPGAs. So you can also do that like a Snickerdoodle. So you can 100% do that. Now, if you're talking about I wouldn't. Those two things are, I would say, like an ARM CPU. They have what they call a microblaze, which is just like a free soft core Cortex M0, or maybe there's a couple different versions of it now that they recently made free, but that you can run as a soft core in the FPGA. So that would work like any normal kind of microcontroller. There's some nuance there, but they have like board support packages and all that kind of stuff where it's only really a few clicks of a mouse button to get that up and running. Now, in a soft GPU is sort of in a different category. That's like a expert level type thing. But you can start smaller. I wouldn't necessarily look at using an FPGA fabric as a GPU. Isn't really the way I would generally look at it. While they're sort of used for quasi-overlapping applications, if you're looking like for parallel algorithm execution kind of stuff, they are kind of analogous, but the GPU is really just a whole bunch of static cores running at the same time, trying to just slog through a bunch of stuff. FPGAs are a little bit different, where it's a little bit more kind of targeted or specific to, say, if you are trying to accelerate an algorithm the same way you would with a GPU. GPU is just like, here, run this as fast as you can. FPGA is more like, I want to take specific components of an algorithm, or maybe the whole algorithm, and turn this into something that the hardware can understand. And you're not really running software at that point. You're just streaming stuff into the algorithm, and it's spitting out an answer on the other side, because the logic that would be built into the algorithm is now built into the hardware. So it's just like it's kind of just all rushing through there, and all that stuff's being executed in parallel in hardware, and that can lead to all the savings and all of the other benefits we kind of commented on before. So the getting into that hardware acceleration piece is sort of the next step, and you can dip your toe into the water with that stuff. Adam Taylor, if anyone's ever heard of the Micro Z Chronicles, it started out he's great. So it started out as focused on the Micro Z, which is some
we did a workshop with him, actually.
He's all, I don't know, that guy is just a
what was the name of that series?
Micro Z Chronicles, MICRO.
I'll bring up
yeah, you find it. Yeah.
I'll bring it up.
It used to be specific to Avnet's Micro Z platform, which is another Zynq-based dev platform. But now he does stuff for all kinds of things. I mean, he has almost every kind of project you can imagine, all open source. Does a lot of stuff on Hackster. He has his own site and everything. He even does stuff with Intel FPGA. So there's a lot of content there.
Yeah, it's for those of you who are interested. Actually, on our YouTube channel, there is, I think, a 3-hour workshop that Adam Taylor did with us last year on FPGAs. So it might be worth having a look there. And I've just put a link to the book in the comments as well that we're talking about here. We've got quite a few questions here that overlap about FPGA choice. So for example, she's scrolling back up, there's millions of these. So we have any advantage of using one FPGA over another than other than the amount of logic cells. And also a comment down here, but in a similar vein, do you have any advantages of Zynq versus Altera, this kind of thing. So when you're choosing, when you're choosing an FPGA for your own use, or indeed for the Snickerdoodle, what are you looking for? What are the different options available apart from, as you say, like the different number of programmable gates?
Yeah, and hey, Drew, good to see you on here. Yes, so there's a very long-winded answer to that. And as with everything, it depends on what you're trying to do. So, if you look up, say, for example, if you go to basically any one of these Xilinx product tables, to be perfectly honest, we have dabbled very little into the Intel land, Intel Altera stuff. Although we did explore quite a bit when we were first evaluating which architecture to go with. I mean, honestly, for us to maybe explain it through our experience when we were first saying like Zynq versus Cyclone, a lot of it, honestly, for us came down to the physical package size. So for the resources that we could get from Zynq versus the Cyclone, it came down. I mean, the area for roughly an apples to apples comparison was almost half with the Zynq 7000 series, what we could get with Cyclone. Cost, of course, was a big consideration, especially for us, because we were trying to make this platform as accessible as possible to people, because that was one of the struggles. Is like, how do you afford some $5,000 FPGA development platform as a hobbyist? It's kind of ridiculous. So so cost and size and some other things. A lot of the more nuanced discussion gets into the actual resources that the FPGA has. So yes, at a very high level, well, depending on how you look at it, at a very high level, logic gates and all that kind of stuff is a factor. A lot of times, honestly, that isn't necessarily the limiting resource for an FPGA. So, like, even for me, I'll get out of my comfort zone necessarily thinking about the very low level specifications that you need to look at. But as an example, block RAM, might be one of as we frequently see is one of the limiting factors in terms of which package to select. The types and number of specific transceivers, the bandwidth that those transceivers have. So if you're doing like PCI Express or multi-gigabit Ethernet and things like that, those kind of high-speed interfaces, usually these FPGAs, especially the SoCs, will have built-in hardened peripherals for those. So it depends now. Like it's one thing to say, oh, we have all these different I/O and I'm just the logic, and we'll just have soft cores for everything. But that's not necessarily always the most economical use of FPGA. So if you can advantage of those built-in peripherals, the better. So you probably could go on, and I'm sure there's like a million different blog posts and stuff, but those are just kind of some of the examples. And happy to chat with people offline as well, or after this or whatever about specific answers. But it gets into some pretty kind of low-level stuff, but it really comes down to what your application actually needs to make sure you're not over or under designing for something.
And also, one of the big considerations at the moment is, can you actually buy the damn thing? You know, yeah. If you can get an FPGA, that is the one you are using. Like,
and it's crazy. Like, we've heard stories about people they'll buy, $500 development boards just to pull off the like $50 FPGA on it so they can stick it on something else. It's completely
I've heard so many of those stories.
Yeah.
I've got another question actually from Drew, which might be a little quicker as well, saying saying the tools for Xilinx are painful to have disk froze for it all. It would be good to know if Ryan has any tips for how to manage a Vivado installation. At the moment, what he's doing is external SSD for Xilinx tools like Vivado when he has to work with clients using Zynq. Do you have any great tips for this, or do you just swallow the disk space on your computer? Like, what's your approach to working with, because I'm imagining you work with a few different tool chains across different FPGAs in your personal work, but yeah, how do you manage that? Any quick tips?
So probably the kind of best and maybe lamest answer is so as you might have already noticed, when you install the Xilinx tools, by default they'll select every possible device they've ever built, basically, that's free and all that, or and every possible option. Basically every box is checked in terms of the capability of the tools. The best thing you can do to save a bunch of disk space is to uncheck a bunch of those boxes. So if you know you're not going to be designing on certain devices, you don't need to support certain packages and all these different things, you can deselect a lot of that stuff. Now, of course, that might change your download or your install, whatever, from like 60 gigabytes to 30 or something ridiculous. So, it's a substantial savings, but it's still absurd and burdensome and all of that. But feedback. Okay.
Apparently there's some feedback again. I've just switched did that fix it? Apparently there's some weird feedback going on, but hopefully that has fixed what was going on. Please let us know if there are further audio issues.
I heard that there was some weird kind of sound, like I was like a mermaid swimming through the ocean there for a second, but I think it's all gone.
How's that though? Well, just pipe up. I did change something, so pipe up if the audio goes again. Nice. Yeah, it's also the battery on these terrible Bluetooth headphones is wearing it. So
yeah. I don't know if that helps at all. I mean, honestly, that is so. We've been talking with Xilinx for years, and I think they kind of started doing this, but not really, about like coming up with some sort of solution that can just be run in the cloud, so you don't have to bother with all this nonsense, like a modern, development company because I mean, the other problem is, and this is like, sort of a word of caution, if you will, for FPGA people new to FPGAs. When you're synthesizing, basically creating a new design that's very large, so you have like a whole lot of FPGA resources that you're utilizing. Those designs, depending on the hardware you're running the software tools on, can take a long time to synthesize, or to generate whatever the output's for, compile, I guess, if you will. So that now, that lends itself even more to saying, like, well, if I have some virtually infinite amount of cloud resources that I could leverage, then I wouldn't need to bother with all, having a ridiculous amount of cache or RAM and all these other things that make those tools run faster. So it's kind of anyway, I'll admit, like, it definitely is a pain point. There's no real easy solution to it, but aside from, you just uncheck all the parts that you don't need to support, as an example, all the part families anyway, you don't need to support when you're downloading it, and it'll go a lot faster and it won't be as brutal. That's about as good as it's going to get, I think.
Yeah, for sure. I've got a couple of more interesting technical questions here. So from Eric J saying, if you can, could you describe the bus data speeds when moving data in and out of the FPGA circuits? I think that would be a nice one to talk about. And then the other one I wanted to ask is, so we announced earlier that there will be more Snickerdoodles coming, and there's questions about which one that you're actually producing as well. So Do you want to take those? So there's the flavor of the board, and then the one that I was interested in.
the bus speeds,
which was the bus speeds,
Yep. So the one, so later this month it'll be the one first. I will say that it's not necessarily going to be later this month, but we do have several hundred Zynq parts now for the black. So we're going to be getting those out as quickly as possible. We have a bit of a backlog with the contract manufacturer and things like that. But so it'll be one connectors up, Snickerdoodle ones in the very near term, and then connectors down, Snickerdoodle blacks and maybe some ups there as well in the I'll just say medium term, near term in the context of you don't have to wait a year for it. So and then we're talking like a couple months hopefully. So in terms of the bus speeds and all that, so there's one of the really cool things about the system on chip model is that, because the silicon physically exists on the same device or same part, there's some super high speed interconnect between the FPGA and the ARM processor. So when I say high speed interconnect, like equivalent to the interconnect on like a microprocessor. So you're never going to outpace the physical interconnect between the FPGA and the ARM device on the actual chip itself. So if you want to look up, you can look up like AXI4, like AXI4 or AXI Lite interface. And there's all sorts of documentation on all that stuff. So that's
interesting.
So there's also what they call AXI chip to chip, which is essentially the same general interface kind of architecture, but designed to go between, say, two FPGAs as an example. Intel has something very similar. So there's also a very common use case, if you will, is moving data, basically having shared memory access between the ARM processor and the FPGA, where the results or outputs of one go into RAM and then the other can access that. So those are all sorts of different, and that can vary. The actual access to that varies on the parts you're using and how the board's designed and what the actual thing's doing and all these other kinds of things. But they're all, generally speaking, it's all you're not generally speaking not going to outrun any of that. And if you do, then there's where you get into keeping that RAM on the chip itself. So you get into the block RAMs, where the less, as people might already know, the one of the big kind of power draws from any embedded system is moving stuff into and out of memory. So the less that has to happen, the lower your power consumption, the higher performance, blah, blah, blah. So that's one of the nice things having those block RAMs is basically memory blobs they're distributed throughout the FPGA, where as much as you can, you want to keep all the stuff that you need on the FPGA, as opposed to going back and forth. So you can buffer video and all the rest, whatever random things you're doing there. So anyway,
yeah, for sure.
Helps,
yeah, absolutely. Really great little piece of information there. I wanted to bring up here, if we can tell us about any applications you've seen the Snickerdoodle used for and how the extensive I/O has been used. Now, I know that you've got a link here to your project. So this is a good, failing to bring that up, 1 second. So there's lots of, do you want to talk about some of your favorite projects that you've seen people, and I will bring this up on screen as well.
Yeah, and just so people kind of have an idea, I kind of glossed over at the beginning, but so you'll see here Snickerdoodle has a bunch of I/O banks, input-output banks. So there's 4 on the bottom here and then 1 at the top. So 5 that are pure FPGA. So those are all 100% software reconfigurable. And then there's another strip of headers over here for the processing subsystem, they call it. So basically the ARM microprocessor. So that's more of like they're quasi reprogrammable, I guess you could say. Now, so we have a connectors down version of the board. So this one has a little heat sink on it, but basically the connectors are on the other side, and that's designed for to go into a baseboard. So as an example, We have like a breaky, so just a breakout board. So you literally.
I love the name, by the way.
Yeah, thank you. This is back right after the makey days on.
I figured.
So it basically just breaks out the I/O into these 0.1-inch headers, so kind of traditional kind of maker headers, if you will. So you can also the nice thing about the connectors up board is smaller form factor, and you can just plug some jumpers that we sell directly into the headers there. So it makes it really easy to kind of go back and forth between different kind of configurations. And as an example, as far as the reconfigurability of the hardware goes, so again, it's using the exact same board. This is our Pi Smasher board, which you'll see on our website and everything. So we have a
also a good name.
Yep, thank you. Probably assume where that came from. So you can just go download on our website an Ubuntu image with all of the peripherals you see here supported on it. And, in about 5 minutes, you go from having all these reconfigurable I/O and a blank slate to now you have dual Ethernet, a bunch of audio interfaces, USB, et cetera, et cetera. So those two are our kind of main development, breadboard, kind of daughter board, baseboard, we call them, kind of things. Some of the other applications, I have a few here, some commercial examples. So these are kind of bigger, so it'll probably block out my face. So this one was for a 6-axis robotic arm project we worked on several years ago. So again,
I'm going to spotlight you so we can see that.
Oh, sure, yeah. So a whole bunch of bulky headers and all that. So this was controlling 6 brushless DC motors and then plugged into some external power supplies. That was for an industrial automation project. We have another here, which there's a little it's a shield over some of the parts here. But so this one, again, uses a Snickerdoodle. It actually also has another FPGA on it. This is a video processing application where we had 16 Ethernet cameras coming into an FPGA on board. It was doing a bunch of tiling and compression and all that kind of stuff that fed into the Snickerdoodle, which was controlling, wireless connectivity, a bunch of LED stuff, again, Ethernet, and all the other kind of peripherals on here. You got some cellular modem. And then another quick one I'll just show off is here's one that was for another video processing application where I don't have the enclosure for it right for any of these things right now, but this could either take in this had HDMI, 1080p HDMI in and out, as well as SDI in and out, and an Ethernet. So what they're doing is some real-time video encoding for a broadcast video application. There's like dozens of other examples. A cool one that I don't know if I have a board handy, but there's a really cool pinball application. So people are into pinball.
I saw that. Yeah.
So yeah, check out scorbit.io. I think is SCORBIT. Super cool product and project with this. Jay Adelson is heading that up. So they're using a Snickerdoodle with their own hardware to basically smartify old school pinball machines. So basically, you take your pinball machine, you plug the display into their board, and another cable goes at the other end to have that display flow through. So you can get these old school dot matrix displays, basically all your score information and all that kind of stuff. That all is piped into the internet where they have the whole back end where you can create a user profile, track your high scores, compete in tournaments, all sorts of super cool stuff. So that's a really exciting project that's kind of just ramping up now that we're looking to support. So yeah, there's all sorts of, it's once you actually kind of get an understanding of when we say reconfigurable, reprogrammable, like it really is reprogrammable. It's like the only thing that's the same basically in any of these applications is the main brain, which is Snickerdoodle. Everything else is like, it's all application specific. So whatever peripherals you need to hang on or hang off the side, and it's designed to go from prototype to production. So that's why we basically created the Snickerdoodle down versions where you plug that into a baseboard. So you have the exact same piece of hardware using for your prototypes as you do when you're building 10,000 of these things, hopefully.
I've got a couple of questions, but I also wanted to say that Eric J, with this comment, you were closest to my timestamp on my piece of paper. So you win today's mystery hardware box, which isn't that mysterious because we all know it contains a Snickerdoodle, at least figuratively. The real Snickerdoodle is currently on in moving, but you also win a very exciting pair of Xilinx socks. Who doesn't love technical socks? A bunch of swag, some breadboard stuff, and a very fetching beer tote. Who doesn't like a beer tote? So Eric J, if you could send me your details either on DM on Twitter, either my personal Twitter, which is Helen Leigh, Leigh, or Crowd Supply, it's crowd_supply. Just send me information and I will get that sent out to you. There will be a slight delay because the Snickerdoodle in question is currently packed because Crowd Supply is moving between offices, but we will get you that Snickerdoodle as soon as we have those boxes in our new space. So please do send me over those. That's actually quite a nice tote. I quite like the beer tote. It's quite funny. And we love the socks. Who doesn't love technical socks? That's always everybody's favorite part of the giveaway. I love a good pair of technical socks. Thank you very much for your question and comments there, Eric J. So I've got a few more questions. I've got loads of questions. I haven't gotten anywhere near being able to pose most of these questions to you because they've been coming in thick and fast today. So before I get onto some of these final questions, how do people reach you? How can people continue to ask questions? How can people continue to be up to date on Snickerdoodle and all these kind of things? Like, are you a social media kind of guy, or are you a little bit of a hermit? What's your GitHub, Twitter? What's your poison?
So I always try to be a social media kind of guy. It's not so much that I'm a hermit. I'm just like I struggle finding the time for it. But I'm on LinkedIn.
All the motivation.
All the time. Yeah, exactly.
You're on LinkedIn. I can't even log into LinkedIn. I haven't logged into LinkedIn for like 2.5 years, I think.
Yeah, so definitely anyone who wants to connect on LinkedIn, that'd be great.
Okay, and you're just Ryan Cousins on LinkedIn.
Yeah, Ryan Cousins. Yeah, you'll find me. There's really only one company called Critical in the world that's spelled KRTKL, so that's a really easy way to find us.
Yes.
So you can follow us there. Connect with me, all that good stuff. Email, of course. So my email is Cousins, my last name, so COUSINS @critical.com. I am on Twitter if people want to follow me for
I did just are you I only found the company Twitter.
Oh, okay, yeah, so there's Critical_Inc, sorry. So we haven't reserved that one yet. So there's Critical_Inc, and then there's my personal Twitter is Ryan Cuz, COUS. So all one word, should be on there. But yeah, it'll probably pop up under one of those.
Oh, I find you. You actually look quite different on your avatar. But
maybe, yeah. It's probably
in real life. Let me just.
But yeah, so those are probably
the
main ones. We do a what do you call it? A newsletter you can sign up for on our homepage. People want to.
Who doesn't love a newsletter?
Here
we are. This is the Twitter.
There you go. Yeah.
We've got a newsletter as well. It's actually one of our most popular. We've got loads of people signed up to our newsletter, but that's probably because we don't spam people. So.
Exactly. Yeah, we are the opposite of spam. We definitely don't send out.
Yeah, exactly. Like the Xilinx updates. We're like, sign up, and you get like 2 emails a year.
Exactly. Yeah.
Or like 4 emails or something. Like it's not very spammy, which is great.
Yeah.
All right, so that's how to find you. There we are. That's very exciting. All right, now let's go back and let's smash out some final questions. So we've got here: are you still building the Pi Smashers? Are there same parts sort of issues? And from the same person, did you consider selling the parts that you got from Xilinx and pocketing the profit instead of building boards?
Okay.
You could have sold them at a massive markup, and then Xilinx would never speak to you again.
Yeah.
But yeah, you'd be able to retire maybe like 10
Yeah.
FPGAs. That's enough to retire at this point.
Exactly.
So you still, let's talk about this Pi Smashers. Are you still building those? Like, what are your plans for the future for this and other boards?
Yeah, good question. I think I saw some question in there about the life cycle of Snickerdoodle. So
exactly, I was about to bring that one up as well. So yeah,
if you go to our website, it's either snickerdoodle.io or I think it's just critical.com/snickerdoodle, whatever. If you go to our website, you'll find Snickerdoodle. It's the biggest thing on there. But if you scroll all the way to the bottom of the Snickerdoodle page, there's it's called something along the lines of like a SOM lifecycle agreement or something like that. SOM being system on module. So that I don't know exactly how many years we are into it, but basically I think it might have been 2016 or 2018 or something, where it guarantees it will manufacture Snickerdoodle in substantially the same form for at least 10 years, or will release the design so anyone can manufacture them, kind of thing. So there's basically a guarantee there. That's like if we go out of business or something. So, which I don't plan on happening. But the Pi Smasher, we are very much still manufacturing everything. So breaky, Pi Smasher, all of that. Pi Smasher, fortunately, we have a whole lot of. And you can go on. And Mauser, I think, has like 200 something of them. If you're looking for one, I think they're probably all sold out on Amazon and all that. But so yeah, those are not an issue. And if people want to check out,
and I really wanted to put this up before we head off, because this is a really awesome talk that Ryan did back in 2018, which talks, I mean, normally we end up talking on the Teardown sessions, we normally get into manufacturing woes, which we haven't gone into too much because we've had so much else to talk about today. But I know that people who are creating their own hardware do like to hear about people's project development process and the things they've done wrong in it, so that they can, learn for their own thing. And this is a really good example of a warts and all tale of bringing a hardware project to market. So I'd really highly recommend that those of you who are interested in that side of the open hardware business should go and check out that blog post. The video on the blog post. So really interesting. I was
going to say we for sure could have filled up this entire time with discussing all of our miserable failures and all that. The time, and the list has only gotten longer since the supply chain stuff started. So that whole talk.
I know. Oh my goodness, I know.
Yeah. So people, check it out. I mean, we've received a lot of good feedback on that one. So
really good. It was an excellent piece of information. All right, so it has always somehow been over an hour that we've been talking. So thank you so much for everybody keeping us company today. We've been absolutely inundated with comments and questions. You're a very popular creator, Ryan, clearly. And you've had some great, I particularly like the opening discussion of FPGAs. So if you are looking to get started in FPGAs, I think you've got some really great advice in this hour long. So Nick, you've asked me if the Teardown sessions are weekly. The answer is sometimes. Yes, they are. They are weekly, every Friday at noon. Who have we got next week? Oh, we've got Joey Castillo, one of my faves, next week, who is the creator of Sensor Watch, and we are going to take a look at what he's been up to. They are not always weekly because I do travel quite a lot for my work, so I'm always off out and about at community events. And sometimes we're moving offices and life gets in the way. But yeah, roughly weekly. So do you I always forget to say like and subscribe, but please do like and subscribe. If you'd like more nerdy conversations with questionable audio quality, I'm your gal. So yeah, so thank you so much for joining us. It's been a really fun session, and I've definitely learned a lot. And there's been some really interesting discussions going on in the chat as well. And so it's been great. So please do, those of you who joined us, please do not forget to go and follow Ryan on the old Twitter and read the blog, check out the GitHub, check out some of the projects that he's done. There's all sorts of things for you to dive into from today's conversation. And yeah, thank you so much for being such a great guest, Ryan. You've filled my brain with delicious information, and I'm very grateful.
Yeah. No,
any parting words for
thanks so
us?
much, Helen, for having me on. And thanks everyone for joining. Great questions. No, I mean nothing really specific. I mean it's obviously some crazy times, and anytime you get your even hands on a piece of hardware, it's kind of, I think, something most people just took for granted. I know I did for all of these years. This was
I know
not being able to get parts was for a long part of our journey not the main issue. It's been crazy.
It's been a wild ride.
Yeah.
Even like Bunny Huang can't get his hands on parts, we're in trouble.
Exactly.
Like Bunny Huang and Lady Ada can't even get parts. So the rest of us mere mortals are scrabbling around and desoldering chips from boards in desperation.
But yeah, I mean, I love everyone's super engaged here, and I really do encourage you, even if it's on a Snickerdoodle, of course, just to get an FPGA, experiment around, learn what they're all about. I mean, they're awesome tools.
It's so fun to play with.
I mean, it's kind of you gotta warn you, it can be somewhat addictive once you actually get into it, because once it starts to kind of click, you're like, this is awesome. I got to do more of this. So definitely encourage everyone to just get out there and make stuff. And that's what it's all about.
Awesome. Well, that's an excellent point to leave this on. Thank you, everybody, for joining us. Congratulations to the winner of this week's hardware mystery / Snickerdoodle box. And I will see some of you next week when I'll be chatting to Joey Castillo. Thank you again for joining us, and goodbye. Have a lovely weekend, everybody. Bye.
Take care.